My name is Chuck Mooney, and this is the first in my practical SEM lecture series, Introduction to SEM and Electron Optics. Why do we want to use electrons for microscopy to begin with? As it turns out, microscope resolution in the far field is diffraction limited, and that limit is about 1/2 of the wavelength of the incident radiation. In this case, the far field means that the optics and the sample are separated by more than the distance of a single wavelength. Photons, as it turns out, have a fairly long wavelength, much longer wavelength than energetic electrons, with the average wavelength of visible light being on the order of 550 nanometers. This means that visible light microscopes are limited to about 250 or so nanometer resolution. You can improve this using scanning and fluorescence techniques, but these are whole topics in and of themselves. And since many current technologies use sub-100 nanometer structures, we have to be able to observe those with better resolution than what we can currently achieve with a visible light microscope. The wavelength of electrons typically used in electron microscopy is on the order of 10 picometers or less, and this includes both highly energetic electrons that we would find in a transmission microscope, as well as the more moderately energetic electrons that we find in a scanning microscope. This means that the diffraction limit of electron microscope resolution is on the order of 5 picometers, which is a factor of 10,000 better than visible photons. And if we recall that the diameter of a carbon atom in a graphite lattice is 170 picometers, this diffraction limit certainly suggests that we should be able to easily image atoms. And with a transmission microscope, we can. In a scanning microscope, the actual resolution limits are defined by the initial spot size, the lenses, and any lens aberrations in the system, with the current limit being on the order of a 1/2 nanometer for high-end SEMs. And I personally suspect that this is a fundamental limit that is defined by the physics of the electron-sample interaction. A traditional optical microscope uses a set of lenses to project a virtual image of a sample onto a detector. In this case, the detector is being shown as an eyeball. But there's no reason that we can't use a camera or a view screen. The important part here is that the entire image is projected everywhere all at once. Almost all photon optical systems work this way. This is the way your eyes work. This is the way optical microscopes, binoculars, telescopes. In fact, you can use electrons for traditional microscopy too. We call that transmission electron microscopy. And in that case, we take a beam of electrons and we pass it through a sample and project an image onto a detector on the other side. But that's not what we're doing today. We're going to be doing scanning microscopy. With a scanning microscope, we do not project an image onto a detector. The image is formed by scanning a probe over the sample one picture element at a time. Scan systems are common. You're looking at one right now. Televisions are, fax machines are. The screen that you're looking at right now is scanning fast enough to give the appearance of a projected image, but that's because it's refreshing faster than your eyes integrate. The scanning in scanning microscopy means that we place our probe at the first point on the sample and we pick up data with a detector. Then we assign that data to the first point on the view screen. Then we move our probe to the second point on the sample. We collect data with a detector there and we assign that to the second point on the view screen. And we continue doing that in a raster pattern. As shown is a digital raster pattern where you scan over, scan back, take a step, scan over, scan back, take a step. And we continue that until we get to point X sub n, Y sub m. And in that way, we build an image one picture element at a time. So my general definition of scanning microscopy is to scan a probe over a sample and to map the position of the probe versus the sample probe interaction, where the image that we display is larger than the region that we scan. A scanning electron microscope is going to scan an electron probe over a small region. An atomic force microscope scans a small physical probe, and a focused ion beam scans an ion probe. In general, with a scanning microscope, the lenses do not form the image. The image is formed by scanning the probe over the sample. The optics form the probe. The optics include the source, the lenses, any correctors in the system, and any apertures that are in the system. The probe characteristics are determined by the parameters for the optics. Electron and ion probe characteristics include beam energy, current, spot size, and convergence angle. With an AFM probe, we have a sharp physical probe instead of a focused charged particle beam. With a sharp physical probe, there are no probe-forming optics. That means that the focus is a function of the shape of the probe. Magnification of a scanning microscope is a function of the displacement of the probe and not the optics. The magnification is determined by the size of the scan pattern, and the resolution is determined by the size of the probe. This means that magnification and resolution are completely independent and have nothing to do with one another. With a scanning microscope, we are going to focus at high magnification and then reduce the magnification to look at the image. This is because focus is scaled with magnification. At low magnification, things change very, very quickly, and at high magnification, the focus changes slowly to allow for fine focus adjustments so that we can see small details. After we reduce the magnification or zoom out, the image will still be in focus. Zooming out or reducing the magnification changes the size of the scan pattern on the sample, but does not change the optics. This is because magnification is not a function of the optics. Magnification is a function of the scan size. We do not change the probe characteristics by changing the scan size. We merely change how far we sweep the beam across the sample. We've discussed scanning microscopy in general. Now let's go scanning electron microscopy in general. In general, with an SEM, we're going to scan a small, round electron probe over our sample. The smaller we can make our probe, the better our potential resolution. We will call the probe, the spot, or the beam, and these terms may be used interchangeably. At each point in our scan, we're going to collect data with a detector. There are many types of imaging data. The most common are secondary electrons. Unless the signal is cathodoluminescence, there is no color. Cathodoluminescence in this case means a cathode ray, which is an electron beam, causes luminescence, which is emission of visible light not from heating. Now, there may be energy information about the emitted electrons, but we don't get color in the traditional sense that you think of with your eyes. We're then going to display the data such that we get a map of probe position versus detector output. And if our displayed map is larger than the area that we scan, we've made a microscope. Here's an example SEM image. This particular image is manganese phosphate coated onto a piece of steel as a corrosion barrier, and it's very clear to see the morphology of the sample. We can clearly see the crystalline structure of the manganese phosphate. Shown here is a schematic of an SEM. At the top of the column, we find an electron gun. In the schematic, this electron gun is represented as a conventional thermal emitter electron gun with a filament, a Waynault cap, and an anode plate that accelerates the electrons down the column. Just below the electron gun, we find the condenser lens set. There's typically 2 condenser lenses in an SEM, which work together. Continuing down the column, we find the objective lens. The objective lens focuses the beam onto the sample. Typically either inside or just above the objective lens, there are a set of scanning coils and also a set of astigmatism correction coils that are not shown. This particular schematic shows a final lens or objective aperture in a real position, which would be in the center of the objective lens. In practice, most of the time, SEMs place the objective aperture in a virtual position between the condenser lens set and the objective lens. We also need a scan generator to generate the scan, and that has to be coupled both to the graphical user interface and to the scan coils. We need a vacuum chamber in which we can locate a sample, typically on a sample stage. We need some sort of a detector or set of detectors, and then the detectors supply information to the graphical user interface. Here is a diagram and photograph of a typical conventional thermal emitter SEM. This is the Hitachi S3200N SEM at the Analytical Instrumentation Facility. And as we can see from looking at the diagram, at the very top of the column we have an electron gun, then there's a set of condenser lenses, there is an objective aperture which is in a virtual position between the condenser lenses and the objective lens. Below the objective aperture we have a set of double deflection scan coils followed by the objective lens. Inside the chamber we have a 5-axis specimen stage and a set of electron detectors. If we look at the outside of the microscope, at the very top we've got the electron gun, and the electron gun is in this general area. Above that there is a high voltage cap because we have the capability of having up to 30,000 volts applied to the electron gun, and a 30,000 volt bias will exceed the breakdown voltage in air and arc. So you have to be very careful about how you deal with that, and usually electron gun caps, the high voltage cap, is a very large assembly. Below the electron gun is the condenser lens area. We can see the controls for the objective aperture. Here are the controls for the 5-axis stage, which are mounted on a door which closes up the vacuum chamber. If we look at the back, we can see this little sliver back here is the backscatter detector. There is an X-ray detector. This little silver tube that's not labeled is the secondary electron detector, and we also have a current amplifier if we want to collect current images. Inside the main chamber of the SEM, we find the objective lens. The objective lens housing is typically called the pole piece. There is also a passive scintillator backscatter detector, an Everhart-Thornley type secondary electron detector, an X-ray detector. In addition to those detectors, we have an infrared camera, which allows us to see inside the microscope, and also a vacuum gauge. These are photographs of the Analytical Instrumentation Facility's ultra-high resolution microscope, which is a Thermo Fisher Verios 460L. The L means that there is a load lock through which you can insert samples into the main chamber without having to break vacuum. This particular microscope is equipped with an oxygen plasma generator, which allows us to clean hydrocarbons off of samples inside the chamber, and you can see an X-ray detector hanging off the back of the microscope. If we look inside the main chamber, we can see what appears to be a much more complex pole piece, and that's because it is much more complex. This part right here is the Everhart-Thornley secondary electron detector. There is a through the lens detector, which is the high resolution secondary detector. There is an insertable backscatter detector, an insertable scanning transmission detector. This is where the sample is located. And if we look in the back of the microscope, we can see the infrared chamber scope. We've mentioned already that we need a vacuum chamber to house the samples in an SEM. So why do we need a vacuum? The primary reason that we need a vacuum is to increase the mean free path of the electron, and the secondary reason is to increase the lifetime of the source, or to even make the source possible. The mean free path of a particle is the distance that particle can travel in a medium without a scattering event. The mean free path of an electron in air is on the order of 100 nanometers. Since we have more than 100 nanometers between the electron gun in the column and the sample, we need to increase our mean free path. If we can pull a vacuum to 10 to the minus 4 torr, we can increase the mean free path of our electron to about 1 meter. And a meter is typically more than the distance between the electron gun and the sample inside the chamber. The secondary reason is for the electron source. Tungsten filaments operate pretty well at 10 to the minus 4 torr. Field emission requires ultra-high vacuum, or 10 to the minus 10-ish torr. What is a torr? A torr is a convenient way to express a vacuum. It's not an SI unit. It was named in honor of Evangelista Torricelli, the inventor of the barometer. It's easy to remember that 760 torr is an atmosphere, 10 to the minus 1 to 10 to the minus 3 torr is a mild vacuum, 10 to the minus 4 to 10 to the minus 8 torr is high vacuum, and less than 10 to the minus 10 torr is ultra high vacuum. And that's the primary reason I use it, is because of the ease of orders of magnitude. The electron optics consists of all the parts that are required to form an electron beam. What we want to end up with is a small, round probe of electrons at the surface of the sample. The smaller we can make the spot, the better our potential resolution. We also need enough current to produce enough signal to be detected, which means that the more electrons we inject into the sample will mean more signal that we get out of the sample. A single electron will not create enough signal to be measured. SEM optics generally consist of an electron gun, the condenser lens set, the objective lens, the objective aperture, and the astigmatism correction coil set, which are also known as Stigmator coils. There are two main types of electron guns, thermionic and field emission. Thermal emitter electron guns are simple and have a very long history. Field emission electron guns are capable of very high resolution, with the limit on the order of a half nanometer. Why do we call an electron gun? Because it shoots electrons down the column, in this case at near relativistic velocities, and anything that fires a projectile is a gun. Thermal emitter electron guns use thermal energy to overcome the cathode's work function and release electrons. The work function is the energy required to liberate an electron from a sample. I like to think of electrons in the sample as water in a bucket of water. So we have a bucket filled with water, and the water comes up to the Fermi level, which is the level of free electrons inside the sample. And the work function is how much energy we have to supply to allow electrons to escape into the vacuum. So if we think about building a fire underneath our metal bucket and heating up the water, some of that water is going to start to gain enough energy that it can escape into the air. And it's a similar thing that happens with electrons in vacuum. This is the most common electron source in SEMs. It has more than a 135-year history. It's also known as the Edison effect and was originally reported by Guthrie in 1873 and described in 1884 by Thomas Edison, although neither one of them really knew what was going on. It's very simple to operate, it's very low cost, and there are minimal vacuum requirements. We're going to literally heat the material until electrons boil off of the surface. The components of a thermal emitter electron gun include the filament, the Waynault cap, and the anode plate. The filament is the source of electrons, and it is generally a piece of tungsten wire that's bent into a hairpin and connected to a filament heating supply. The filament heating supply is connected through a bias resistor to the Waynault cap, which is also called a Waynault cylinder or grid cap. And the Waynault cylinder is a simple electrostatic lens that forms our first crossover. It creates these series of electropotentials, and it forces the electrons into the first crossover. The other thing that it does is it suppresses emission everywhere that's not at the apex of the filament. The anode plate is going to accelerate the electrons down the column. Unfortunately, this particular drawing is horribly misleading because it shows electrons coming off the apex of the filament, going through this cute little crossover created by the electrostatic potentials of the Waynault cap, and then passing harmlessly by the anode plate on the way down the column to the sample. Good, bad, or indifferent, the vast majority of electrons that come off of the filament strike the anode plate and are lost. So we lose most of the electrons that we create with the filament before they even go down the column, typically by orders of magnitude. We typically measure emission currents on the order of tens of microamps, and we typically measure beam currents on the order of nanoamps to picoamps. To put together what we talked about in the last slide, we're going to take current from a power supply and flow that through a tungsten filament. Resistive heating will cause the filament to get hot enough that electrons literally boil off the surface. Those electrons are then accelerated towards a more positively charged anode plate, and the Waynault cylinder acts as a simple electrostatic lens to form the first crossover. These are the physical components of a thermal emitter electron gun. We have a filament. The filament is typically spot welded to a couple of conductors so we can pass electricity through a ceramic, which you cannot see, that's inside this aluminum housing. You can see a set screw that's used to position the filament under the Waynault cap. You need to very precisely position the apex of the filament underneath the hole in the Waynault cap in order to get the electrons to go down the column. Here is a Waynault cap. The Waynault cap screws onto the filament holder. You can see the threads on the filament holder where this will screw on. And all of that fits together as a single component, which fits into the high voltage cap of the SEM. Here is an anode plate. This is typically the size of the width of the column. The hole in the center is for the electrons to go through. These other large holes are for vacuum conductance. Shown here is a typical tungsten filament. The tungsten cathode is approximately 100 micron diameter tungsten wire that is bent into a sharp hairpin. It is directly heated through resistance heating. The emission area is on the order of 100 by 150 microns. And this is not a round point-like source. So in order to make a microscope, we need to make the electron probe as small and round as we possibly can. Our typical operating conditions are that we're going to run at about 2700 Kelvin. Filaments fail, and they must be routinely replaced. Don't worry, our typical lifetime is on the order of 50 to 250 hours, which is usually somewhere on the order of a couple of weeks to a couple of months of actual operating the microscope time. The filament that's shown on the left failed through normal means, through normal heating. You can tell that because you can see faceting on the filament surface. The filament on the right was overdriven. It was heated too much, it was overheated, and it just blew up very, very quickly. And you can tell that because you don't see any facets on the wire. In fact, you can still see the drawing marks on this wire. And that is a clue that it didn't have enough time to preferentially evaporate tungsten along particular crystalline planes. Both of these failures were hot, and we can tell that because we've got a little molten ball at the end. If you have a cold failure, then you'll have a fracture surface. Here are a couple of representative SEM images from a thermal emitter SEM. The image on the left is coral with some diatoms on it. This was collected at Hatteras by a graduate student many years ago. This particular image was taken with a 20 kV beam, and it's at 2,000 times magnification. The image on the right is a section of a steel sample that has been polished, and you can see a calcium carbonate spherical inclusion with a triangle of magnesium oxide in it. This was from a senior design project in material science and engineering several years ago. With a field emission electron source, we apply a very high electric field to a sharp needle-shaped emitter tip. The shape of the sharp needle concentrates the field and creates conditions that allow for quantum mechanical tunneling of electrons outside the sample. There is no classical analog. A convenient way to think about this is to imagine that we have a barrier between our emitter tip cathode and the vacuum. If we apply a very high field, we can distort the shape of the barrier such that the barrier still exists, but it's thin enough that electrons from inside the emitter tip can tunnel into the vacuum, where they can then be accelerated down the column by the anode plates. Field emission achieves very high resolution because the electrons tunnel out of a so-called virtual source that's very small with a diameter on the order of 10 nanometers. This means that we do not have to demagnify the source very much to have a very small spot size. Recall that smaller spots allow for higher resolution. There are several varieties of field emitters. There are cold field emission electron guns, thermally assisted field emission electron guns, and Schottky emitters. Schottky emitters are a special case. Most people refer to them as field emission because everybody knows that field emission SEMs have the best resolution. However, in my not so humble opinion, and I admit that my opinions about SEM ceased to be humble many years ago, a Schottky emitter is a field-assisted thermal emitter. Let's take a look at the energy diagram. If the Schottky emitter is going way out here like this, that is far too great a distance for the electrons to tunnel from the inside of the emitter tip into the vacuum. They have to be liberated through some heat. The design of the electron gun and the emitter itself is another clue. The emitter uses a zirconium oxide coating to reduce the work function, and the electron gun itself employs a suppressor cap similar to a Waynault, which suppresses emission of electrons everywhere but the apex of the tip. Field emission is hard. It is much harder than thermal emission. It requires a much better vacuum. It's much more difficult to build a reliable electron gun. The geometry has to be extremely precise. You cannot change the emitter tip itself in the field. You change the whole electron gun assembly. The microscope is down for 3 or 4 days while you do this. It takes about 30 minutes to change a thermal emitter. If it blows out, you change it yourself. You don't call a service guy. So why do we go through all the trouble? The reason that we go through the trouble of doing a field emission SEM is because the electrons in the beam come from a very, very small virtual source. It's on the order of a few nanometers for a cold field emission SEM and less than 50 nanometers for Schottky emitters. And if you recall that the thermal source size is on the order of 100 by 150 microns instead of nanometer scale, then you realize very quickly that we're looking at multiple orders of magnitude in size difference for different sources. And this means it's much easier to do high resolution because we already have a very small spot. And also, and this is sort of an aside that doesn't have much to do with practical SEM, but it's nice to know that field emission and Schottky guns have so-called very high brightness. This means that more electrons per unit area are emitted, and as the thermal emitter is made smaller and smaller, the number of electrons in the beam becomes so small that no usable signal can be obtained from the sample. And this also means that current density can be extremely high with a field emission SEM, which means that sample damage is also a potential problem. The components of a field emission electron gun include the emitter tip itself, and generally a couple of different anode plates, and this is for a cold field emission electron gun. We'll have a sharp needle-shaped emitter, and then there'll be a couple of anode plates that are each powered a little bit differently. The idea is that the first anode creates a very intense electric field, which allows the electrons to quantum mechanically tunnel outside this tip. And the second anode plate works with the first anode to create this first crossover here, and it also works with the first anode plate to accelerate the electrons down the column. Here is a physical example of a cold field emission SEM emitter, and it's simply a piece of tungsten wire that has been electrochemically etched down to a very, very sharp point. That piece of tungsten wire is then spot welded to another piece of tungsten for support. In a cold field emission SEM, you typically have to do what's called flashing the tip once a day, and that means you pass a current through the support piece of tungsten in order to heat up the field emission tip itself and boil off any crud that has settled on the tip out of the vacuum. A Schottky emitter tip has a different geometry from a cold field emitter. This tip is typically fabricated by using a cold field emitter tip and then coating it with a layer of zirconium oxide. If you read about this in the literature, they call it a zirconium oxide well. Looks like a coating to me. I suspect the reason it's called a well is that when the well runs dry, the emission becomes unstable. And this means that when the zirconium oxide becomes extremely thin, because remember, this thing is running hot. It's running at a couple thousand kelvins. And so the zirconium oxide is going to evaporate away. And once it evaporates away, the emission becomes unstable. As I mentioned before, a Schottky emitter has to have a suppressor cap. Here's a diagram showing a suppressor cap assembly, which looks awfully lot like a Waynault cap. The suppressor cap suppresses emission from everywhere but the apex of the tip, which suggests that a Schottky emitter is a thermal emitter that is field assisted. This is one of the first 1,000,000x SEM images I ever saw taken live. It is from a gold on carbon resolution standard, and it was collected with a Hitachi S5200 cold field emission SEM, which is an in-lens type SEM. We'll talk about the different lens types in just a couple of minutes. If you look at this, the bright particles are gold, the dark background is carbon, and the smallest particles of gold that are visible are on the order of a 0.5 nanometer. Here is a 1,000,000x SEM image that was taken of a gold on carbon standard, and it was collected with the AIF's Verios 460L SEM. The gold particles are bright, the carbon background is dark. You will notice if we look over here that we can see two gold particles that have a 0.6 nanometer spacing between them. Over here there's a giant rock of gold that's all of 6.4 nanometers across. Please notice that the software guys give you more significant figures than are significant. There is no way that this is accurate to a half of a picometer if we have half nanometer resolution at best. So please report only significant figures and not whatever the microscope's software spits out at you. The Verios is a Schottky Emitter SEM, and it has an immersion lens type SEM. Here is another 1,000,000x image taken with the Verios 460L. This is a 10 on carbon resolution standard. Again, the 10 is bright, the carbon is dark. You notice that these are theoretically spheroids, but these are small enough that they must be single crystal. Notice that there's some roughness on the surface, and that roughness is very likely local oxides because this sample is stored in air. Given the amazing resolution that we can do with a field emission SEM, why don't we make all SEMs field emission? And the simple answer is cost. Thermal emitter SEMs are typically on the order of $150,000 to $250,000 when they're pretty well decked out. You can get a low-cost example for less than $100,000. Field emission SEMs start at $500,000. High-end models are typically on the order of $1 to $2 million. The Verios 460L was listed at $1.5 million when we bought it several years ago. And why are the difference in cost? The simple answer is that field emission SEMs require much more expensive equipment, and they're much more complex. You have to have ultra-high vacuum for the electron gun. And whenever you see the abbreviation UHV all in a row, you should read $, because ultra-high vacuum is expensive and difficult to attain. It requires additional equipment. You have to have much quieter, higher-end electronics. The whole vacuum system is much more complex. The lens is cooled with a high-end chiller that only varies by 1/10 of a degree. The system is typically fitted with a complex vibration isolation system, and there's additional maintenance that is required. Typically a once-yearly bake for good vacuum, or some sort of gun conditioning or gun replacement is required. Field emission SEM microscopes are down a whole lot more often than their thermal emitter counterparts because of the complexity. And also, if you consider many samples just don't require super high resolution and magnification. Thermionic SEMs can be made to work very well up to about 50,000 times magnification, although your low-end models will top out at about 10,000 in terms of usable magnification. And most SEM images are still less than 10,000x. The people who are taking really high magnification and want super high resolution are people who are studying solid state interactions and solid state things that are going on where they need the material science size features. People who are doing biology and looking at industrial samples, those tend to be much, much larger. Now we're ready to talk about electron lenses. In a typical SEM, there are two sets of lenses. There is a condenser lens, which is typically a set of lenses. There are usually two of them that work together, and there is an objective lens. The condenser lens set is going to determine our spot size and our current. We have to recall that the initial spot crossover has a finite size, and the condenser lens is going to demagnify the spot. As our spot size decreases, the current is also going to decrease. The smaller the lenses can make the spot on the sample, the higher the resolution that can be achieved. But we have to remember that we need enough current to create signal. There's usually two condenser lenses that work together, although I know of at least one SEM that has three, and I know of at least one that only has one condenser lens. The objective lens is going to focus the probe on the sample, which means we're going to force the probe into a small, round spot at the surface of the sample. Electron optical lenses in an SEM are usually electromagnetic, and that means that we have windings of copper wire or a coil inside an iron housing. We're then going to pass current through the coil in order to create a magnetic field. An electron passing through the magnetic field will change its direction based upon the field strength, and the field strength is proportional to current flow. So the more current we flow through the magnet, the stronger the lens will be. An example of a lens is focus. When the focus control is changed, the current through the objective lens changes. It is possible to make electrostatic lenses, but the geometry and control are much more complex. Electrostatic lenses can be very powerful. They're typically used in focused ion beam systems because it's easier to make a high-strength electrostatic lens than an electromagnetic lens. They're not that common in SEMs, although they are becoming more common with immersion lenses. Electrons passing through an electromagnetic lens will follow the Lorentz force law, which I'm sure we all recall with great clarity from freshman physics. The Lorentz force law means that the force on an electron passing through a magnetic field is equal to the charge on the electron times the cross product of the velocity vector of the electron and the magnetic field vector. The Lorentz force has two consequences. Electron lenses are always convergent. The B field forces electrons to the center of the lens. We can have divergence only after a crossover. It also means that electrons that aren't exactly in the center of the optics spiral down the column. If we're at the position of the sample and we look up the column, it will appear that electrons are going around in circles. The length of the column is insufficient for a complete revolution, but if we change the strength in one of the lenses, that's going to cause the image to rotate. An electromagnetic lens in an SEM is typically an iron housing that contains windings of copper wire. So if we take a look at this schematic here, we can see an iron housing, and the iron housing has windings of copper wire. All of these circles represent a single winding. There is a gap in the iron housing. The magnetic field emanates through the gap. The electron travels through the bore. The bore is the center part of the lens. The lenses are typically rotationally symmetric so that you would have a round lens that's shaped somewhat like a donut. All the lensing action happens in the gap. An electron comes through the bore, and once it reaches the gap in the lens, that's where the magnetic field is, and that affects the path of the electron. One of the consequences of the Lorentz force is that we have to worry about aberrations. In theory, all of the electrons are accelerated exactly the same by the anode plate, and they all have exactly the same energy. The energy is expressed as the velocity of the electrons. However, there are going to be some small differences between electron energies in the beam. So if we have a delta in the velocity of our electrons, that's going to result in a delta in the force that's experienced, which means that electrons with different velocities get focused to different places, which is like not being in focus. This is called a chromatic aberration, or C sub A. The other type of aberration we have to worry about with the Lorentz force law are spherical aberrations. And this is because the B field varies radially across the bore of the lens, which results in a delta of the B field. And this can be complicated if there's a fault in the lens itself that changes the field. A delta in the B field, or the magnetic field, will result in a delta in the velocity, which means that electrons going through different parts of the lens will get focused to different places, which is like not being in focus. This is called spherical aberration, or C sub S, and this is a difficult aberration to deal with. In general, we're going to have both chromatic and spherical aberrations present in our system. So the delta in the force that the electrons experience is going to be both a function of the delta in the velocity between one electron and another, and the delta in the B field as we go radially across the B field. SEM designers lie awake at night trying to figure out how to minimize these aberrations because they reduce your resolution. Both can be corrected. Neither is generally corrected in a conventional SEM. Some SEMs have delta V correctors that reduce the delta in the V, and this is called a beam monochromator. Some TEMs have C sub S correctors. Our Titan TEM has a C sub S corrector. However, cost and SEM resolution limits have kept these off of SEMs thus far, and quite frankly, I don't expect to see them on an SEM anytime soon. Some ultra-high resolution SEMs are equipped with a so-called beam monochromator. In the Verios 460L, this is called the upper corrector. The upper corrector is a slit-type monochromator that is designed to limit the energy spread in the beam. In theory, a monochromator only allows a single wavelength or energy to pass through. Good, bad, or indifferent, an energetic electron's wavelength is so short that there's still an energy spread, but it's reduced by about a factor of 10 in current designs. Beam energy is a function of the exit angle from the emitter, and the energy typically varies by plus or minus about 1 eV for a Schottky emitter. At low voltage, this creates issues with respect to chromatic aberrations, or C sub A. C sub A is caused by different energy electrons being focused to different places by the same strength B field. The upper corrector works by electronically blocking the hole in the anode plate that electrons would normally go through, forcing those electrons through a small slit that is off to the side. The slit is an order of magnitude smaller than the hole in the anode plate. Only the electrons that pass through the slit can make it down the column, and those electrons should have a smaller energy spread than those that go through the main hole in the anode plate. This is going to reduce the energy spread in the beam by approximately an order of magnitude. So we're looking at about plus or minus 1 eV uncorrected and about plus or minus 0.15 eV corrected, according to published data. The downside is that beam current is variable depending on how you align it, and you can only force so much current through the little slit. On the Verios 460, the maximum current is 25 picoamps. That said, at low voltage and low current, use it if you got it, because it will make your images better. Shown here is a schematic of the operation of the upper corrector. The uncorrected condition, shown on the left, is typical for an SEM. In this condition, there is a wide angle of emission from the emitter over which the beam energy can vary. If we reduce the size of the aperture in the anode plate, and the way that we do this is we electronically block the standard hole in the anode plate, and we force the electrons to a slit that's off on the side. The slit is an order of magnitude smaller than the hole in the anode plate. This reduces the spread in the beam because we are looking at only a very small angle of emission from the emitter. And all of the electrons that are emitted at the same angle should be very, very, very close together in beam energy. Good, bad, or indifferent, my art skills are not well developed enough to make the slit appear to be an order of magnitude smaller than the hole in the anode plate. But it is. Since the corrector aperture is so small, there is a limited amount of current that we can force through this small aperture, and so only small beam currents are allowed when the upper corrector is activated. The primary role for the condenser lens is to demagnify the initial crossover. The first time I heard this, I thought to myself, demagnify? I thought microscopes were supposed to magnify things. But in practice with a scanning electron microscope, we're going to scan a small, round electron probe over the sample. The emission area for a thermal emitter SEM is on the order of 100 by 150 microns, which would lead to very poor resolution. So we want to demagnify the initial spot as much as possible in order to get good resolution. And we not only want it to be small, but we also want it to be round, because a non-round spot will give us a distorted image. In a modern SEM, the condenser lens is typically a set of two lenses that work together in concert using a single control. The designers of the microscope should program the control to operate both lenses in concert so that the operator doesn't have to worry about having to optimize each individual lens. The control is typically labeled beam current, although it could be labeled spot size, CL, or condenser, especially in old school microscopes. As we increase the current through the lens, the current in the beam decreases and we get a smaller spot size. It's important to keep the current straight in your head. Lens current is the current that's passing through the coil lenses, and that changes the electromagnetic field strength. Beam current are the number of electrons that strike the sample per unit time. The condenser lens system does two things. It demagnifies the initial spot, and this is done to improve resolution, and it's really what we want. The second thing that happens is it's going to limit the beam current as electrons that strike the inside of the column are lost. Imagine what happens as we increase the strength of the field in this lens right here. As we increase the current through the lens, the strength of this magnetic field will increase, and that will cause this crossover to move up in the column, which will make these angles more sharp. As these angles become more acute, more electrons are going to strike the inside of the column, and they are not going to go down through all of the various spray apertures to strike the sample. Those electrons strike column parts and go to ground. When I worked for an SEM manufacturer in the 2000s, we came out with a microscope that could go through 2 orders of magnitude of current without changing the beam current. And at first, that boggled my mind. I couldn't understand how this followed the laws of physics. And after I thought about it for a while, it occurred to me that all we were doing was throwing away beam current. The initial spot size was so small that the condenser lenses really weren't demagnifying it very much once we reached a certain point, and all we were doing was throwing away current. There are several types of objective lens. The most common is the pinhole type lens. A pinhole type lens is shown in schematic form on the left, and a photograph of one is shown on the right. And this is the most common type of lens that you'll find in an SEM. The lens is at the bottom of the electron optical column, usually in the vacuum chamber, and the sample sizes are limited only by the size of the chamber and the stage. And there are SEMs with chambers that are large enough that you can literally walk inside it. This is an example of a giant sample SEM. This is the sample chamber. It's hard to appreciate the scale of this, except to note that this port cover right here, this window, is 2 meters above the floor. So the total height of this particular chamber looks like it's on the order of 12 meters. This is a giant vibration isolation leg. There are 3 of them that can lift the chamber up off the floor when it's being operated. If we look inside the microscope, you can see the electron optical column is supported on a slideway, so it can move side to side and up and down. Here is an image of the bottom of the Electron Optics where you can see the pole piece. This is a X-ray detector. This piece right here is a backscattered electron detector, and this guy is a secondary electron detector. Here you can see an operator positioning the microscope close to part of an airplane. This looks like part of an engine for an airplane. And since you don't want to necessarily cut the engine up to take a look at it, they put the whole thing inside there, position the microscope very carefully, because this part right here needs to be about 15 or 20 millimeters from the piece that they're going to look at. Then they close the door and evacuate this whole giant chamber, which I imagine takes some time before they can start looking at the sample. The very first ultra-high resolution SEMs employed in-lens type objective lenses. A schematic of such a lens is shown. With a lens like this, the sample is placed inside the lens using a TEM style sample holder. This means that your sample sizes are severely limited, with a 3 by 5 by 1 millimeter sample being considered a bulk sample for an in-lens SEM. What happens in a microscope that employs an in-lens objective lens is that the electrons are focused onto the sample inside the lens, and emitted electrons spiral up the column where they are detected inside the column. The big problem I've always had with this type of objective lens is that the wonderful thing about an SEM is that you can put fairly large samples in them. You don't have to make your sample so small. If you're going to go ahead and make your sample small enough that it'll fit on a TEM style holder, I've always thought, why not take the extra step and thin it down so that it's electron transparent so that you can get real high resolution inside a transmission microscope. The reason to use an in-lens objective lens is to immerse the sample in the magnetic field of the lens. Having the sample immersed in the field reduces the influence of external fields, which can distort the beam after it exits the magnetic field of a pinhole type lens. Being in the field also allows for much better beam control and higher potential resolution. Immersion lenses, a schematic of which is shown on this slide, were developed to have the best of both worlds, the potential for both a bulk sample and the ability to immerse the sample in a magnetic field from the lens. Electrons in the field spiral back up inside the column where they are detected by an in-column detector. Electrons outside the field can be detected by detectors inside the chamber. With many microscopes, it's possible to turn the immersion lens on and off so that you can have low resolution mode with the immersion field off and high resolution mode with the immersion field on. The downside to an immersion lens SEM is that ferromagnetic materials cannot be observed in high resolution mode because they are lifted off the sample holder and deposited onto the lens, which is bad for the lens. I mentioned earlier that if we change the strength of one of our lenses, that will cause the image to rotate. This is because of the Lorentz force law. The cross product in the force law means that as the magnetic field strength is changed, the image will rotate. So here we can see the effect of going from a focal length of 35 millimeters to a focal length of 10 millimeters. You can see how much rotation we had. This is a function of the Lorentz force law and a direct effect of that. In addition to lenses in the electron optical column, we also have apertures. Consider that an electron beam is Gaussian in nature. At the center of the beam, most of the electrons are going to be very close in energy to one another. At the edges, the electrons are going to have slightly different energies, and they're going to be at a different place in the B field of the lens. So what the aperture is going to do is it's going to reduce the far off axis electrons. This is going to have two effects. One is going to reduce the energy spread of the beam because we're only going to be using the electrons that are closer to energy with each other in the center. And it's also going to reduce spherical aberrations, or C sub S, which is caused by the magnetic field varying across the bore of a lens. A beam passing through a small aperture will have a lower current and a better potential resolution than one passing through a large aperture or no aperture. The apertures in the system, and the objective aperture in particular, serve several purposes. They remove off-axis electrons, which reduces aberrations. They increase the potential depth of field, which is a pure geometric effect. They're also going to increase the potential resolution by reducing the aberrations in the system. The objective aperture is generally changeable, which means that there's a strip that has multiple apertures on it that allows the operator to choose a particular aperture depending on what they're trying to do. In general, we're going to use a large aperture for X-ray analysis because we need current. We're going to use small apertures for imaging because this gives us better geometry and it reduces aberrations. But you must notice that small apertures are going to limit current and signal, which means we're going to have to count longer. So we're going to have to collect our images over a longer period of time. So now we can think about what the whole goal is of the entire electron optical column. The point is to place a small round electron probe at the surface of the sample. The smaller and more well-defined we can make our spot or probe, the higher our potential resolution. Let's put the electron optics together. At the top of a conventional thermal emitter SEM, we have a cathode filament that supplies electrons, a Waynault cap that forms our first crossover, and an anode plate that accelerates the electrons down the column. We have a set of condenser lenses that demagnify the initial spot and limit beam current in the sample. We have an objective lens that focuses the final spot onto the sample, and it typically is going to contain Stigmator coils, which are going to correct the astigmatism in the beam. We're going to have an objective aperture to remove off-axis electrons, but we still haven't formed an image. We've made a small spot onto the sample, but in order to form an image, we have to put in a set of scanning coils and scan the spot over the sample and collect signal with respect to the XY position. In order to construct a map or an image of the sample, we scan the beam over the region of interest on the sample. Beam deflection coils, which are electromagnets, are used to move the beam across a sample and typically in a raster pattern. So we place, as we talked about at the very beginning, we place the beam at the point x1, y1, and we collect signal. We display that signal intensity at point x1, y1 on our monitor, and we repeat until we get to point x sub n, y sub m to build an image. For microscopy, the size of the pattern on the screen should be larger than the size of the pattern on the sample. The deflection coils are typically arrayed in a double deflection design. So you first deflect over and then deflect back. This allows you to make a larger scan on the sample while going through a relatively small objective aperture. We're going to scan the beam over the sample to make a map of the image. The larger we make our scan, the lower the magnification. So as we decrease the scan size, we increase the magnification. More current passing through the scan coils is going to result in more beam deflection and a larger scan size. The magnification control changes the current through the scan coils and changes the magnification of the image by adjusting the size of the scan. Focus should be an easy concept. If the image has sharp, crisp edges and you can see detail, then we consider it to be focused. In practice, humans are comparatory creatures. We have to compare things to understand what's bigger or less. So in order to focus, you have to see the image out of focus. That means that blurry features are brought into focus by going through focus in order to observe where the features are crisp and sharp. You cannot sneak up on focus. You must boldly go past in order to observe where it is the best. This means that when you're turning the focus knob, you don't know if you turn it a little bit more that it's not going to continue to get better until it starts to get worse. Focus is complicated by astigmatism in the beam. Non-roundness in the beam is called astigmatism. The initial spot size formed by the Waynaut cap in a thermionic SEM is generally not round. Our emission area is on the order of 100 by 150 microns, which is not a round point-like source. And so this non-roundness continues all the way through the optics to the sample. In a field emission SEM, the initial spot size is theoretically symmetric, but non-roundness is introduced by imperfections in the anode plates and lenses and continues to the sample. In both cases, astigmatism correction is critical for high-quality images. Shown here is a schematic of a typical octopole astigmatism correction unit. Each one of these is going to have 4 north-south pole pairs. Each north-south pole pair is going to create a magnetic field, and the octopole is going to allow us to create an asymmetric magnetic field in order to correct astigmatism in the electron beam, which means that we're going to force the beam to be round as we pass it through the center of the octopole. There is an astigmatism alignment which puts the beam at the center of the asymmetric field, but astigmatism alignment does not correct the astigmatism. It merely places the beam in the center of the asymmetric field. If the beam is off-center from the asymmetric field, when you adjust the field strength in the octopole, that's going to cause the beam to get pushed around and the apparent image will shift. So if you don't like shifting images when you're correcting astigmatism in front of your microscope, you want to do the astigmatism alignment. But note that will not correct astigmatism. At focus, an astigmatic beam will produce a fuzzy image that appears to be out of focus. If we focus above or below the sample, the projection of the beam can appear to be elliptical. This will result in different resolution in different directions. Along the short axis of the ellipse, we will have sharp, crisp features. Along the long axis of the ellipse, we will have blurry features. By switching between focusing above and below the sample, the astigmatism can be recognized and corrected. Here is an example of an image collected with an astigmatic beam in an overfocus or focused slightly above the sample condition. If we look in this direction, everywhere we look, we see sharp, crisp edges. In the orthogonal direction, all of the images look blurry and stretched out. That means that we have an elliptical beam with this orientation. If we now focus slightly below the sample, which means that we have an underfocus condition, the opposite has happened. In this direction, which used to be sharp and crisp, it's now blurry. And in this direction, which used to be blurry, all the edges are sharp and crisp. Let's look at that again. Here is our overfocus condition, sharp features in this direction, blurry features in this direction. focus below the sample, and we get the opposite. Blurry features in this direction and sharp features in this direction. In order to correct astigmatism, you adjust the focus such that all of the features look equally out of focus in all directions. And then we adjust the two astigmatism coil correctors. There's going to be one labeled X and one labeled Y. And once we adjust those, we're going to look for detail. Look at how sharp and crisp the edges are over here compared with our original astigmatic image. If we have good focus and bad astigmatism, the image is going to appear to be blurry and out of focus. When we adjust the astigmatism, we want to look for detail. Let me show you the sorts of detail that I look for. There is a spot just above the laser pointer that is sharp and crisp. If we look at the corresponding area in the astigmatic image, if you use your imagination and squint, you can see that there's a little smudge just above the laser pointer. Look back at the good image. Just above the laser pointer is a sharp, crisp little detail. It's a little piece of steel on top of a latex sphere. Here is the same feature in the astigmatic image, and if you again squint and use your imagination, you can see a little smudge. Here's another couple of little features on top of this latex sphere, and they look sharp and crisp. Over here, we just see a smudge. This feature in the image that is uncorrected looks like nothing. And when we look at the image that's astigmatism corrected, it appears that someone has pitched a tent on top of an asteroid. So we're looking for detail when we adjust the astigmatism. And that concludes the lecture on electron optics and the introduction to scanning electron microscopy. The next practical SEM lecture is on signals and detectors. This has been a very brief introduction to SEM electron optics. There are great resources out there, including Goldstein et al., if you want to learn more.